Today's seminars. Today's speaker is Professor Saku Tsuneta. He's professor of the National Astronomical Observatory in Japan. He has worked on developments of space-based instruments for the Japanese solar physics spacecrafts like Hinode in 1981, Yoko in 1991, or Hinode in 2006. He's also leader of the Hinode project in Japan and PI of the Hinode Solar Optical Telescope. But besides instrumentation, he made also lots of important studies using these instruments. His scientific interests cover a broad range of topics in solar physics, including particle acceleration, magnetic reconnections in solar flares, coronal heating, and magnetic field dynamics in photospheres. So thank you for giving us the talk.
Okay. Thank you very much for the nice introduction. Today I will discuss about some aspect of the Hinode data. And the title of my talk is Quiet Sun Magnetism and Alfven Waves as Observed with Hinode. And I like this picture, this white light, quiet sun. It indicates many things. The sun is just a star with hydrostatic equilibrium, essentially, and spherical symmetric. But nevertheless, as this picture clearly shows, we have a very strong magnetic field that's represented by sunspot. And the fundamental question we have to pursue in solar physics is that how is this magnetic field generated, transported, and how it is used to hit the chromosphere and the corona. And the sun has a very strong magnetic field on its surface, 1 kilogauss, which exceeds the equipartition field. If you go to the bottom of the convection zone, people believe that we have a field strength of 100 kilogauss, which also exceeds the equipartition field strength. And if you are away from the sun, if you go to the pulsar, 10 to the 12 kilogauss, 10 to the 12 gauss, which is probably due to the compression and the fossil field. But if you go to the magnetar, which has 10 to the 15th gauss, and we need a dynamo here again to explain this very strong field. And if you go backward, the galaxy and cluster of galaxy has a magnetic field strength 1 to 10 microgauss, and which is extremely strong if the magnetic field of the early universe, like the reionization phase, is 10 to the minus 15 gauss. There is no mechanism to explain this strong magnetic field with a simple omega mechanism of galaxy rotation, Kepler rotation. So in general, we can say that the magnetic field in the universe is very, very strong as compared with the local equipartition field strength. So we want to learn why this happens using the sun. Sun is the only target which we can see very clearly. The general question, one of the questions here is how does the universe create strong field? By fossil field, alpha omega oscillatory dynamo, turbulent dynamo, or convective collapse. And this is a review on the role of magnetic field in stars and cosmos. And there obviously magnetic field plays a very important role in astronomy. And highlight in the word is a keyword in this talk. Magnetic fields are created by interaction of flow and fields by global process or local process, dynamo process. It carries energy through waves and fluctuation. It can store energy, of course, and it dissipates stored energy with a process called magnetic reconnection. It induces magnetic MHD instability, current-driven instability, and eruption from the sun, such as CME, is a result of this instability. And it suppresses cross-field transport for mass and heat, of course. It's plasma is magnetized, and it suppresses convection, therefore we have a dark sunspot. And let me briefly talk about the history of solar physics from Japan. It started in 1981 with the launch of this small spacecraft, which carries a hard X-ray imaging instruments. And this is followed by Yoko 10 years after, which carries both hard and soft X-ray telescope. And this was quite successful. And this is followed by Hinode, and where we, for the first time, has a very high resolution visible light telescope. So as you can see, there is a very natural extension of the science front from 1981 to 2006. And we want to continue this beyond, based on the result from Hinode, based on our heritage. And this is Hinode. And the objective of the Hinode is systems understanding on the generation, transport, and ultimate dissipation of the solar magnetic field. Magnetic field can dissipate with time scale much faster than the time scale determined by Spitzer conductivity. With three well-coordinated telescopes. Those are solar optical telescope, imaging spectrometer, UV imaging spectrometer, and X-ray telescope. Let me stress that Hinode is not a Japan-only mission, and international collaboration is a keyword always. And we deeply appreciate the contribution from the United States and ESA, which provides a vital ground station in the northern tip of Norway. And all the data of Hinode is taken here in Norway and sent to JAXA by internet every day. So it involves three space agencies, ESA, JAXA, NASA, and 11 organizations in 4 countries to build a solar bee over 8 years. This is a snapshot on a visible light telescope when it is completed in our observatory, clean room. And it has a highest spatial resolution, and the ground-based, I should say, the ground-based champion data of the ground-based telescopes here in Canarias has higher spatial resolution, but the uniqueness of Hinode is the continuity and the uniformity of these data, and stable point as a stable point spread function. And wide field of view to cover the active region, and 24 hours continuous access to the sun. These are the features that makes Hinode visible light telescope very unique. And this is a snapshot during the construction of the telescope at NAOJ with industry partners, which is Mitsubishi Electric. This is a construction of the telescope. This is a thermal vacuum test with many optical equipment to check the diffraction-limited performance in a space environment. This is the sunlight. We have a natural sunlight introduced to the clean room, and this was very, very useful test to check the performance of the telescope as a system. And this is the telescope and the focal plane package provided to NASA and Lockheed Martin. We are deeply involved in the construction of this part as well, but it is essentially built by Lockheed Martin in California. And this is delivered to NAOJ, and this is our clean room, and that was put on the optical bench of the spacecraft, and everything is integrated electrically, optically, and so forth, and the final check was done using the actual sunlight introduced to the clean room, 50 centimeter wide sunlight. And then telescope was delivered to ISAS, and everything is on the spacecraft and launched on that day very beautifully. And let me repeat the basic question we address: how is the solar magnetic field generated and transported? And as important as this is the conversion of magnetic energy to create X-ray corona flares and eruptions with this term. This term is very important. And magnetic field dissipate, and this is the result of it's a corona, and it's spatially, temporally quite non-uniform. The X-ray corona is bright, where the magnetic field is strong, namely the active region. Even without a strong active region, we have X-ray corona everywhere on the sun. And this is a zoom up of the quiet sun, just one portion of the sun. And again, we see the non-quiet quiet sun, X-ray corona. And these are X-ray resolved X-ray bright point. X-ray bright point is resolved with Hinode for the first time. It actually consists of the very complex bipole structure seen everywhere in the field of view. In addition to this bright point, we see more fuzzy dim structures like cloud that covers the whole field of view. Conjecture is that even in this fuzzy structure consists of these X-ray bright points. We don't know. Next frame shows the photosphere of this size. But before going to that, this is a textbook description of the solar atmosphere. Everyone knows that. The previous movie shows the solar atmosphere of this region, corona. The next one shows the solar atmosphere of this region. What I want to stress here is that the distance between this and this, the distance is just 2 granule size from here to there. It's very short, so it's a very high gradient system, of course. And this is a G-band image taken with Hinode. But my point is that size of the granule is like this. So the corona is located here, but the 2 granule size away, 1, 2, the solar corona starts here. This is 6,000 K. This is 2 million K and beyond, and connected to interplanetary space. And there are many elementary flux tubes, mainly located in between the granular cell. These are essentially vertical, and it is connected to the corona, of course, and that should play a role in the coronal heating. And this is just pay attention to this magnetograph image, and those magnetic dots are moving due to the quasi-stationary or random motion of the photosphere. And it is interesting to track from its birth to this in a Lagrangian way to check what Parker said is correct or not. And this is a cartoon written by Parker, and we are in a position to check whether this is right or not by using the previous image. That has not yet done, but this is one of the things that we have to done to check whether this is correct or not. This is a very interesting idea to be confirmed or rejected by observations. And the flux comes from below. So this is one of the most interesting data taken with Hinode, I think. The flux emerges to the surface with a small, in the form of a very small flux tube, thin flux tube. And if you track, this is complex. And a lot of disappearance is taking place. The flux survived, not reconnected or submerged, which is the end point and form bigger clusters here. So it is very interesting to track the individual emergence and the individual movement of these flux tubes, and to see to understand the overall emergence process. And this finally evolves to the sunspot like this, which has very strong field. Previous one has a somewhat weaker field, 500 Gauss, 400 Gauss. The field strength of this is more than 1 kilogauss. So what is the process in between from the emergence to the formation of the big sunspot, which has a much stronger super-equipartition field strength? And this is a paper by Nagata-san, and the question here is that equipartition field strength corresponding to the photosphere, this is just a 500 Gauss. And whatever the dynamo, whatever the amplification mechanism is, we cannot go beyond this if we follow the induction equation. But observed field strength is as strong as 1 to 1.5 kilogauss. So there is another mechanism other than dynamo to explain this amplification. It is a mechanism so-called convective collapse. And a theory was developed over the years, starting from Parker and many, many people. And it's this is a cartoon to explain this. First of all, some mechanism, any mechanism can amplify the magnetic field strength up to 400 Gauss or 500 Gauss, or this may be the result of emergence of the field. And this field is strong enough to suppress the convective heat input so that radiation cooling takes place, becomes dominant, and scale height becomes shorter and evacuated, so that as a result of a lateral pressure balance, the flux tube is squeezed, and the flux tube with field strength 1 to 2 kilogauss created as a result of this. So this is a process, and we actually found this, and this is the time, and this is the field strength starting from just 500 Gauss, equipartition field strength. It's steady, and suddenly becomes 2.0 kilogauss, and essentially stays there. In association with this, we have a downflow close to sound speed and some rebound and goes back to normal. So this is very much consistent with the prediction, and we think that finally Hinode discovered convective quarks. And Dr. Nagata mentioned this is not a unique process. This happens everywhere on the sun. You can easily find a process similar to this. Sometimes time evolution is more complex, but essentially this is taking place everywhere on the sun. So this is a process to create a 1.5 kilogauss field from 500 gauss. So if you have a convection, if you have a vertical flux tube, I think this will happen anywhere in the universe. And this is a snapshot of the white light convection pattern. And we have a usual Stokes V image indicating a vertical field toward you, away from you. And we have a very strong field, 1 kilogauss. And this tiny dot is not a noise. It is a real structure close to the spatial resolution of the telescope. So plus and minus polarities are scattered all over the quiet sun. We have a larger concentration here and there, and we are familiar with, essentially. But the surprising thing is that linear polarization map, initially reported by Bruce Wright, 2007, as a part of the initial paper of Hinode. And we have a more uniform distribution, ubiquitous distribution of something which produces the linear polarization. And the size distribution is more uniform. And these larger concentration correspond to the field of the vertical flux. So essentially, the size is comparable to the size of the granule. And we now know that the lifetime is comparable to the lifetime of this granular motion. So this is a snapshot, and we have a movie to see how it evolves. And this green one is a vertical flux, Stokes V, with some threshold. And Stokes V, representing a vertical flux tube, essentially located in between the granular pattern. The yellow one is the horizontal field. It appears somewhere inside the convective pattern and disappears somewhere. So we are working hard statistically clarify the location of emergence and location of disappearance and relationship between Stokes Q and the Stokes V to better understand the magnetic structure of the this horizontal field. And this is a summary of the observational property in terms of more prototypical emerging flux driven by Parker instability, where we have a downflow, and so that the instability takes place, and bipolar emergence appears as shown in the previous movies. But I should stress this process is completely different from this in the following respect, and size of this is always smaller than granule. We checked 100 events, but without exception, size is limited by the size of the granule. If this is a part of the sea serpent, it can be bigger, but it is constrained by a single granule always, without exception. One thing which don't understand at all, and we want to have a better understanding with more data analysis, is that the foot point is not clearly seen in some of the events. We thought this should come with a foot point, Stokes as represented by Stokes V, but sometimes it is open-end without any Stokes V signal. Here, we always have a strong Stokes V, and some have a Stokes V indicating the foot point. So since divergence B equals 0, and I think we have not yet clearly understand the magnetic structure of this interesting creature. And regarding the motion of the flux tube, we have a clear upward motion in this case, but there is no velocity difference or a very small velocity difference with respect to the rising motion of the non-magnetized convection motion. So the delta V between this and this is almost 0 or slightly plus. And so there is an enhancement by buoyancy, but essentially we can say moves with the convective flows. This is a PDF, which is a field strength versus a number of pixels. And if you compare the horizontal field, transient horizontal field in the quiet sun and flat, it's same. This is the total flux. We have a peak at 1.5 kilogauss as a result of a convective flux. But we have a mask to choose the horizontal linearly polarized light only. Then there is no difference between quiet sun and polarity region, although there is a factor of 8 difference in the amount of vertical flux in this particular case. And this is a sine plot of the polar region, and we can essentially say that the P-ref of the horizontal field is similar between these two regions. There is slight difference here, but we think there is some contamination of a vertical flux here. So what is the mechanism of to create the horizontal field? And we have 3 significant observational features. Field strength smaller than equipartition field. I forgot to say this. Equipartition field is about 500 gauss. So the pixels, number of pixels smaller than 500 gauss exceeds 90%. The 10% of pixel has only flux larger than 500 gauss. So we can essentially say that the horizontal field has a field strength weaker than equipartition field strength. So, and no preferred direction. We check the direction using Stokes Q and U. And same occurrence rate between quiet sun and the active region. So is this a debris of active region? Some form of debris? Is this a failed emerging flux, failed to emerge to the surface? This is explosion of the rising flux tube as initially predicted by Fernando Moreno and Celtis. And it comes from the vertical flux. Since this is weaker than the equipartition field, it can be tilted due to motion, or it is purely local process, local dynamo process, since we have a lot of rotation V, so that this can be at least a candidate for dynamo process, purely local, not global. So we don't rule out other possibilities, but this is consistent with all the observed features. And we have to be more specific what this local dynamo process means. Nevertheless, we say that the discovery of a transient horizontal field indicates the first discovery of local dynamo process in astrophysics, namely in the solar convection zone. So if we have a convection zone with very small seed field, I think that produces, the system produces a magnetic field very close, with field strength close to the equipartition field in anywhere in this universe. So this is a summary of observations which I said, so I don't repeat that. One thing very interesting to me is that before the Hinode launch, Javier Teofilo Bueno in Nature paper said that quiet sun is covered with a weak field of about 100 gauss, depending on the model, and called hidden magnetism. And this is our PDF, and there is a turnover at around 100 gauss, 150 gauss. And we don't think this is a real feature. We have a stringent threshold to avoid the contamination of noise for inversion. So we are losing sensitivity here, around here. And this may be the same thing. So the question is that transient horizontal magnetic field, what I call THMF, the tip of the iceberg for hidden magnetism. But implication is very important. There is an analogy between the microflare, nanoflare heating to the corona. The analogy is that if this is steep enough, and if you multiply this by b square, we can know where the energy is located. And indeed, in this case, as far as horizontal field is concerned, weaker field has more energy as compared with flux tube with larger magnetic field strength. So energetically, this contributes more than this region. So assume that this extends further and further toward the weaker region. This contributes more energetically rather than this kilogauss field. So, yes. The magnetic field. Mm-hmm. Mm. Yes, I think I may be a little bit misleading in the sense that we intentionally pay attention to the horizontal field only, and it has to be understood as a system. Mm. Yeah. I don't have a nice, in my polar region paper, yeah. I don't have a good chart, sorry. But as far as the vertical field is concerned, larger flux tube with larger field strength has more energy. But as far as the horizontal field is concerned, flux tube with weaker field has more energy. So there is clear distinction. Yes? Yeah, maybe understand. Yes. Okay. Okay, I understand your point. And let me move to the chromosphere. This is a very interesting movie taken by Hinode. There are a lot of dynamic activity here in the form of a fountain-like feature and jet-like feature. And this happened outside the penumbra in the active region. And we want to better understand what is the driving force of this. And because this is a dynamic motion, I think magnetic reconnection has to be involved in the process. To have magnetic reconnection, we have magnetic field, a different macroscopic magnetic structure, and the collision of that will produce inevitably magnetic reconnection. So far, before the discovery of this horizontal field, since I don't know the magnetic structure well at this point, horizontal field is represented by this sign. And before the discovery of this, the solar corona consists of this vertical flux tube canopy structure here. But with this, there are more possibility of having magnetic reconnection between the horizontal field, between vertical and horizontal field. And this is a site for energy release and dynamic motion. And this is purely the conjecture, but since we now know the existence of a nucleature on the solar surface, but we discovered horizontal field here, and we don't have any piece of evidence that this horizontal field reaches this site, where the energy input is necessary. To maintain the chromosphere, we need this amount of energy. To maintain the corona, we need a similar amount of energy. And if we calculate the total flux, assuming of the horizontal field, assuming that it reaches the chromosphere, it amounts to 3 to 6 times 10 to the 6, comparable to this value. Again, I should stress we have a rather high cutoff threshold. And if we go to weaker arm, this increases because weaker field contributes more to the magnetic energy. And let me move to somewhat different topics, polar region of the sun. And this is the X-ray image taken with Hinode to clarify that solar polar region is not a compressed, it's flow of dynamics in the form of, again, jet, for instance, here, and microflares to show the bipolar structure. And the solar polar region is unique because of the following apparent reason: source of the first solar wind, location of the global poroidal field. We can see the poroidal field look like in the polar region. Think of the meridional flow, probably. And we see this polar region with SOT, field of view SOT is as small as this, as compared with the large field of view of the X-ray telescope. And this is, since every foreshortening effect is significant, so that to see the data from the observed frame is highly misleading. To understand the distribution and the shape of the magnetic field, we have to move to this coordinate. So this is the sun looking above the South Pole. We chose the season to see the South Pole as clear as possible using the 7-degree tilt. And we reached the South Pole indeed, although we are losing a spatial resolution. But this is 85, 80, 75, 70 degree. And the polar region consists of 2 parts at least, actually 3 parts, 2 of which are shown here. A very strong vertical flux that coincide in position with polar faculae. But this size is 5 arcsecond by 5 arcsecond, larger than the size of the pore. But this is not the pore, and sunspot does not seen in the dark feature. This is the polar faculae, probably. And the size becomes smaller with lower latitude. In addition to this scattered kilogauss field, we have a weaker horizontal field seen here. All these are horizontal field, which would be the same as the transient horizontal field seen in quiet sun and active regions. And I explained this. It has a similar PDF. And I checked the polarity of these vertical flux tube. In the quiet sun, it is pretty well balanced. But in the polar region, one polarity is dominant. Due to technical reason, there is a polarity of the opposite side, but I don't know whether this is real or not. It may be, one polarity may be more dominant. But in any case, as compared with the quiet sun, polar region, one polarity is dominant, so nothing new. But for specific field strengths, one of the magnitude higher flux in the strong field region, in the polar region, as compared with the quiet sun. So people may have an impression that the coronal hole or polar region has a weaker field, but actually it has a stronger field, no doubt. And in the quiet sun, we have a pretty good balance in the polarity, but if you have a threshold like this, South Pole is dominated by one polarity. This is the summary. I covered this. And this is the X-ray observation. This is the best possible temperature obtained for coronal hole using the eclipse, which is used for calibration. The temperature of coronal hole is 1 million K, and that of the quiet sun is 1.5 to 2 million K. There is also a density difference obtained from a emission measure. Coronal fields do have a lower plasma density, so the pressure is factor of 2 smaller in the coronal hole. So why is coronal hole maintained against the pressure of the quiet sun? The answer is magnetic field pressure balances the compensates the smaller plasma pressure in the quiet sun. So the magnetic observations and the coronal observation, Hinode, is consistent. And so this is the picture emerged from Hinode observations. This may be trivial or maybe more fundamental. In the polar region, we have a feature like this. It is essentially unipolar. And the first solar wind comes from this tiny patch, kilogauss patch, whereas in the quiet sun, most of the flux is closed, and the only fraction of the flux tube is connected to interplanetary space. And we obtained flux and so forth, and this is the best estimate of the total magnetic flux in the polar region. But I can skip this. One conjecture I want to stress here is the propagation of Alfven wave to the corona. Assuming that first solar wind is accelerated by Alfven wave, that Alfven wave has to come from a photosphere. And if you have a straightforward flux tube, most of the waves are reflected back following the principle of optics like this. But assume that we have a highly expanding feature like this, and we are in a stratified atmosphere. Density changes rapidly with height. Magnetic field changes rapidly because of this canopy structure. We have an expansion factor of 1,000 between here and here because single polarity dominates in very low in atmosphere. we have ultimately same expansion factor here, but higher in the atmosphere. It changes gradually. Here, there is no obstacle to stop this. So the inflation takes place lower in the atmosphere. And because of this, Alfven flux can propagate to the corona because of the weaker discontinuity here. So that solar wind plasma that will become first solar wind come from this. Also that supplies that serves as a channel to provide sufficient Alfvenic energy to the corona. This is purely a conjecture at this point. And so the topics moves to the Alfven waves. And my student, Dr. Okamoto, found a transverse emitted wave. Everyone looked at this image and feels very nice. But he's the only person who pointed out something is moving up and down and concluded that this is a very clear signature of a transverse Alfven wave kink mode oscillation of the flux tube. And indeed, you can clearly see that something is moving up and down. And we considered various possibilities. The only conclusion is this is a linearly polarized Alfven wave or kink mode oscillation of the flux tube. And the oscilloscope type description clearly indicates a sine wave waveform, so that all the parameters are obtained: period 3 to 4 minutes, amplitude, and pointing flux to be carried by this wave is 10 to the 7th. So we have sufficient resources to hit the corona. So we say we have a sufficient flux, but this does not mean this is dissipated in the corona. This is a totally different story. And then we move to the photosphere. We have a counterpart to be detected by spectro-polarimeter, because unless we have a dispersion, we confirm the dispersion relation, we cannot tell exactly what this wave is. So this is a magnetic field fluctuation, spectra, and velocity fluctuation, intensity fluctuation. And in longer peak, a longer period, we have a peak. This represents a gradual rise and fall motion. So we should pay attention to shorter wave. Between 3 to 5 minutes, or you always find a very sharp peak. Width is governed by natural width, namely the duration of the observation. And this peak coincides in time, frequency with the velocity perturbation. This particular case, we have two peaks, and again the frequency matches. And we sometimes see the intensity fluctuation as well. And we have two possibilities. One is kink mode oscillation. One is compressive magneto-sonic oscillation. This is more compressive. And I initially thought this is not compressive at all, but people point out this is weakly compressible. This is the intensity fluctuation, the function of number of events versus intensity fluctuation. It essentially says that we have more number of events with lower intensity fluctuation. So this is more kink mode type oscillation, because the intensity fluctuation means the density fluctuation. If you go to this direction, we have a more intensity fluctuation, sometimes exceeding 1%. We initially thought this is a sausage type oscillation, because this is a first order effect, this is a second order effect in a sense. But then our referee points out a very important paper by Komento-san, who points out opacity effects. And this intensity fluctuation is due to the opacity effect. So we are discussing with her about this possibility. We know this possibility almost a few weeks ago. So before that, we simply interpreted this as a signature of a kink or sausage mode. We are interested in the phase relationship between velocity perturbation and magnetic perturbation, because this tells the direction of waves. It's 180 degrees, it's moved this way with respect to magnetic field. If it's 0 degrees, it's moved this way. This is for kink mode case. In the sausage mode case, there are different phase relationship. But if we concentrate on this, there is little intensity fluctuation. So this is almost a pure kink mode. it can be always a superposition of the kink and the linear superposition of kink and sausage. So if you choose, for instance, this event, we thought we can tell the direction of the waves. And this is the period concentrates 3 to 5 minutes. There is no power between 3 minutes. And phase is concentrated minus 90 degrees, not 0, not 100 degrees. So without knowing the Komenko-san's paper, we thought this is a superposition of upward moving and downward moving kink mode waves. We have a line formation layer, we have a reflector here, and minus 90 degree or plus 90 degree indicates almost perfect reflection of the waves. Now we have to check the sub-opacity that 90 degrees due to the opacity effect. But I should stress data is not exactly the minus 90 degree. It has a spread. So deviation from minus 90 degree indicates the leakage to the corona, pointing flux. And this deviation from 90 degree by 10 to 20 degrees is enough to provide 10 to the 7 cells pointing flux to the corona. So this is an important topic to know what amount of transverse magnetic energy is propagated to the corona. So this is close to the end of my talk. I expect many important topics observed with Hinode. High coronal turbulence and penumbral microjets and many different type of reconnection events and supersonic downflow and slow solar wind and so forth. All are connected to reconnection, dynamo, turbulence, and waves, and the coronal heating and chromospheric heating. So finally, this is the history of collaboration between Spain and Japan. I am the first person to reach this country as early as 98. I made the seminar, presented the seminar in 1908. No one remembers this probably. And there is a visit to Japan by Spanish scientists every 3 years, 4 years up to this point until 2007. Following that, it's rapid. There are more and more exchange of people up to now. And this is my 1, 2, 3, 4th visit to Spain. And this is another activity. Do you remember who this gentleman is? This is Valentin Martinez-Piret in 20 years ago. He's a little bit, this is Russia. This is Jose Carlos del Toro Iniesta in 1995 or 1997. And these are recent picture in Granada. And this is Javier Trujillo son in Japanese restaurant. And this is David Ozorko. So my second summary is that looking from Japan, Spanish solar physics has led solar physics in the world in a sense, in various advanced Stokes polarity technique, instrument, and theoretical researches. And solar physics in Japan, people in Japan desires to have a closer collaboration with Europe, especially Spain, for ongoing Hinode and future programs. This is our desire. Okay, so this is final. I don't explain this, but this is so nice. So during discussion time, I continue to show this prominence movie. Okay, thank you very much.
Thank you for your talk. We have now time for questions or comments.
Yeah, I should go back to this interesting.
I have a okay. I have a question concerning this convective collapse that you. This is an instability. So you start with a situation where you have that the structure is stable, which you perturb, and then if you have a given perturbation where the mass go down, you increase the field strength. But if you have a perturbation where the plasma goes up, the structure disappears. So my question is, have you observed this other possibility? I mean, let's say 500 Gauss structure, which dissolves, they come together. I mean, if you have instability going in one direction, you should also have the other one.
thinking
the disappearance, I mean the decrease of the field strength of a structure of 500 Gauss due to convective collapse.
reverse process.
Yeah. The two of them come together.
I think this is an important question in the sense that after the discovery of this, Dr. Nagata concentrated on a theoretical interpretation of this profile. I think this is not the right thing to do at this point. This is just one example. We should analyze more cases of changes of magnetic field, statistical approach. And data indicated this is a clear case, just easy to interpret case. There are more complex cases, many. And that may contain different physics, potentially. So we are in a very early phase of the analysis on the evolution of this flux field. So I cannot respond to your question, but this is more general situation of the Hinode. And evolution of this kind, I have another example my student is doing. It's much more complex, involving a multiple flux tubes interaction and supersonic field and increase or decrease of field strength and formation of G-band bright points. Those have to be clarified by statistical analysis, first of all. Yeah.
More questions, comments?
Maybe this, just a comment to this. I think this idea of the symmetry between the downflow and the upflow, so the downflow would reinforce, the upflow would destroy the structure, goes from the assumption that you have a vertical field, a vertical flux tube in equilibrium. So this is a very theoretical assumption. I don't think there are vertical flux tubes in equilibrium in the photosphere as such. So it's much more likely, I think, that when you have a vertical concentrated structure, it's actually downflowing anyway. So probably there is no symmetry in that sense.
More comments or questions? So then let's thank the speaker again. Thank you.